First of all, hello everyone. Thank you, Jen and Austin, for organizing again this summit and invite me to talk a little bit about the things that we love so much. My name is Irulanducci. For those who don't know me, I'm from Argentina, so trying to understand my English, my English accent and things like that. And like I mentioned before, I'm going to try to explain how the horizons behave, works, or a better way to understanding what happened in the horizon. And that's why, because when you're trying to, for example, access to sites like Wikipedia and trying to find evidence, not real proof, not concrete proof, but evidence of a spherical Earth, the first one is going to be related with the object Earth, because every time that we talk about the flat Earth and versus a globe Earth, immediately a lot of people jump directly to the heavens, and the heavens, space, cosmos, whatever you want to call it, it's not access. You cannot access to do physics there. Nobody can access to do physics. Nobody can access and touch the object there and measure and do, material stuff there. So the first topic always is the objects that supposedly go beyond the curve, and it's going to be obstructed by the geometry of the Earth, and of course the well-known boat over the horizon. In fact, if you and I think this is a new one, because someone at the Lake Pontchartrain, or how I cannot pronounce it very well, but someone add this because this is a new thing. And if you go a little up at the beginning, you're going to find the history behind the globe, but you're going to have this type of, I don't know if it's in this page, you're going to have this type of example where they're trying to convince you that you can, have hidden objects on the horizon due to the curvature of the Earth. And they use GIF animations, and they trying to pursue you to believe that the only, and that is the important thing, the only, the only way that this could happen is because the curvature of the Earth. And we're going to try to at least understand what's going on here. And there is no, this is very simplistic way to trying to understand or explain. Of course, in the past, maybe when you don't have the correct technology and the optics and all the things that we have today, even as a civilian, to put this into a test, maybe you believe it. 100 years ago, people are not so, they don't have so much equipment to do this type of observations, and well, could work, the boat disappear, and could be the geometry of the curvature of the Earth. But in our days, we have much better equipment to put on the test. So that is the idea behind this presentation. First of all, we need to understand that when someone tells you that, okay, if the Earth is flat, we must be C forever, until the edge of the Earth. In fact, if I remember correctly, there is, I think it's here in the English version, that they talk about, on the flat Earth without obstruction, the ground itself will never obscure distant objects. It will be possible to see all the way to the edge of the world. This is how crazy and how stupid people are in the 21st century, right? To the edge of the world is something amazing. So the air itself, beyond the gases that compound the Earth, create the what we call air in terms of what we breathe, is full of water. And this is just a given thing, everybody knows that, but for some reason they don't take into consideration when they're trying to explain how the horizon works. But the whole atmosphere is full of water. In fact, they told us that if all the water in the atmosphere raining down at once, it will only cover the globe to a depth of 2.5 centimeter, about 1 inch. It's like a diluvian, but in the modern age. But the idea is there is water. So if there is water in the air, we're going to have some effects that we need to take into consideration when we're trying to explain why we cannot see forever. And in fact, you don't even need to see forever. You just need to put on test with trigonometry, some object in the distance, and just check that. So first of all, this is what it's called Fata Morgana. It's an old Italian word for describing what in our days we call refraction, diffraction, reflection, etc. But in this case, just to explain this behavior on the atmosphere. Of course, you're going to have on the ground, in the desert, on water, lakes, etc., etc. It's something that you cannot avoid because the atmosphere is full of water. So if you want to recreate this in controlled manner, like the scientific method proposed, we can understand what's going on and why objects disappear in the horizon. First of all, this is a controlled environment. This is a device that use heated carbon nanotubes to create a mirage, and we can see the waves and how these little tint black carbon nanotubes, when it's injected with different water, different heat water, you're gonna see the phenomena that happen in reality, where you have this gradient, in this case coming from back to front, making disappear because there is like a balance, and the heat in the nanotubes is going to equalize the IOR, the index of refraction of the medium, in this case the water. So you're going to have this behavior when things appear to disappear in this linear gradient in the distance, as it happened in real life, as we see, for example, in this type of environment, with objects appear from the nowhere, and you can start see, okay, that is a car, or what, that is a building, or whatever. So of course, I think everybody knows, but this is a nice example to start understanding what's going on. The time, the temperature, the air pressure, all those conditions you need to have into account when you're going to make an observation. Because, for example, this is the same ice piece of land, but in different time, with different atmospheric conditions. And if someone goes and take a picture, in this case, maybe he believes that the curvature of the Earth is obstructing the possibility to see beyond this piece of land. But in fact, if you go in a different time stamp, you can see that the whole complete land is visible. So there is no any type of curvature. It's just how the atmosphere works, and that you need to have into consideration. That is why in our days we prefer observation with infrared and trying to be more high than the ground level, like in the plane, like Jay Toland, that we're gonna see in the future in this presentation. Another way to understanding, for example, this is that the refraction is not a geometric obstruction. Refraction is just that, is this type of dynamics that produce in the atmosphere. Here you have two examples again. It's the same type of lighthouse, but in different times hour. And you can see, for example, in this case, you can see the base, the complete base of the lighthouse, and a couple of hours later, you don't see anything. It's just the mirage and just this tiny part of the top of the lighthouse, of course. Because why things disappear in this gradient line, or in this gradient elevation, is because of the angle of attack and how the light behave in a narrow angle distribution, etc. We're going to see in the future. But the idea here is that you need to take all these type of things into consideration. For example, Wolfie 6020 once showed this image, this video that he took itself, and he proposed that the lighthouse is cut because the curvature of the Earth, which is insane because it's not even inclinated, but you can see what's going on. In fact, time to time we see in the news the famous ghost ship or things like that, that things are floating in the air. And it's crazy because what we are looking here is that, in fact, the horizon is not disappear, or the limit of the horizon is here. In fact, the water is continue really, really far away. And for the condition of the Earth in this case, and the daylight and all that kind of stuff, we can see not the water, of course, because the water is mixing with the sky, but we can see an object that it is in the water beyond what we see in the horizon. And that's crazy, because if we can see how the ocean in this case will be there, is going to be to something that shock you, because you're going to see a lot of water beyond the common horizon. Then we have another example when you can see the same effects of disappearing this gradient line forward to backward in this case, or from here to the back or to the front, sorry, depends of the perspective you want to see it. But what I'm trying to say is that this boat, which is going to start disappearing like the nanotubes that I showed before, it's going to disappear in this gradient manner. Of course, here is the real horizon. We have the bottom mirage, but the boat is going to completely disappear in this type of gradient, is enter in this area of full distortion or full diffraction. You cannot bypass diffraction, and here you can see how the boats disappear. So that is why, for me, it's really crazy that they're still trying to explain, and the most direct observation of the supposedly curvature of the Earth, which is not a direct observation because we are using this indirect method, but they're still trying to explain based on this boat disappearing. Now, to understand a little better, you need to have some things into account. For example, what we're trying to say is that for that phenomena happen, the object must be all in the same plane of view. Plane, of course, it could be a little high, a little low, but in terms of where is the camera, we have the Earth in the middle, and then we have an object that cannot be obstructed and then reappears up for us to see in perfect way with a little of distortion. You always have the object in the same quote-unquote line. When you're trying to recreate this in a controlled environment, here you can see this recipient that contains water, salt, and sugar inside of the water to simulate all the the 5, 10, 20 kilometers of air compressed in one small space. But you're never going to see this type of behavior that they're trying to tell us, for example, in this case with the Canigou. And here you can recreate all the Fata Morgana examples, the superior mirage, the double superior, the inverted superior mirage, the lower mirage, etc., etc. And here you can see how easy it is, but always the object must be in the same line of view. And that is the key. Here we have a real nature example. Here we have a heliocentric drawing because they cannot show in other way. And here we have a control environment, and this is the type of setup you need to use to recreate this. Here you have, for example, a superior inverted mirage of a mountain. The mountain, of course, is in the same plane of view. This is 20 kilometers in this case. But I think you understand what I'm trying to expose here, that the object must be there all the time. Maybe you cannot see it because the fog in the air, but the object is there. And in fact, that is where some stories of the people that work in the sea are believed, that we see, you know, these monsters in the lakes and things like that. So a lot of people say that come from this Fata Morgana effect, where you can have a tiny, maybe shark or whale or whatever, you know, extending and deforming and things like that. So continue with this. Again, you can recreate, we can prove, and we can recreate all the atmospheric phenomenon in the lab, in a controlled environment, and then we can test and put, you know, in the round of compare to or with the nature, and at least we can do that. They cannot recreate what they say that supposedly it happened, where we have cases where you have like 500 meters and even more of occlusion, and supposedly the objects rise up and appear to our eye level to see the majestic of the curvature of the earth. Here we have, for example, from a movie, and this is to illustrate how the angle of attack, it's really important to take into consideration, where we have the old Twin Tower. This is from the movie Thomas Crown, I think it's called in English. And here we can see some buildings in the distance, in the middle of Manhattan skyline. And the camera is a crane camera that is going to go from up to the bottom and trying to film the face of the actor. But when the camera changed the angle and trying to lower the angle, here all these buildings are going to disappear completely. It's going to mix with the horizon and with this gradient line of narrow angle of view. And that is what happened in our world. So you cannot say that the only way that an object disappears is because the curvature of the earth, because you need to have all this type of thing into account. Of course, the Glovers never going to address this topic in this way, because they don't have nothing to prove, to explain, to show, right? So this is how perspective works, but this is in the case of just a geometric world, and we don't live in a geometric world only. We live in a world with optics involved. And when we talk about optics, we talk about how light behave, how the medium where the lights pass through is going to affect the end result that we perceive in our eyes, or a camera, or whatever optics you want to use. Of course, in terms of the trying to see long distances, the best thing that you can do is go higher and use our modern day technology like anti-fog or infrared filters and things like that. And again, you can see a lot of these, I think they do on purpose, but I remember a time where it was this supposedly proof that the curvature of the an object can appear from nothing, from bottom of the obstruction, and see. Let me recap. We see this example where a Glover trying to prove that you can have an occlude object for some geometry, whatever. In this case, is this Bhutan tank, and if the atmosphere behave in certain way, you can see things beyond this obstruction. I hope you understand what I'm saying. Sorry, because sometimes I lost in my real-time translation. But he points the camera to the Bhutan tank, simulating the curvature of the earth, and this is supposedly like a building in the distance, and we only see here the green part of that. And when he drops nitrogen, I think it's nitrogen, we can see a red part that is occluded by this tank. But where is the trick here? Well, we have a lot of problems. The first problem is that we don't live under nitrogen in these conditions where it's almost like a mirror. It's all like a glass. It's like a glass. It's crazy because it's so cold that when interacts with the air in this temperature, is going to act as a glass, that we don't live in these conditions. But the tricky part is that the setup is not analog to the curvature of the Earth, and even in what they propose, because what they propose is that you are in a position where you have the abstraction of the curvature of the air, and the other object is lower than where you are. And this guy made this type of setup. I recreated in 3D. I'm not going to, I'm going just to show very quickly for you to see. I recreated in 3D. I use to model the video. I show the setup. I create the material, the shaders, using ray trace simulation, putting all the index of refraction, trying to recreate the effects on the of the gas, on in this case the nitrogen, things like that, and prove that I can simulate. I can do things like appear the red part, and when with the nitrogen is only the green part. But why that happened and why I recreate that using the same analogy? Because the tricky part is, like I mentioned before, is in the setup. This object, it's not beyond the same line of the horizon. In fact, is on top, and the camera is pointing from the bottom to up. So here is not analog to what supposedly they're trying to prove. And in fact, this is just a tiny 1 centimeter obstruction. And in some cases, we are talking about entire buildings of high 500 meters. So I just showed this because I want to, present what the Glovers, or why the Glovers are so desperate that they trick people. They're trying to lie to people. And of course, people that don't have all this in mind could be misleading, right? We have a nice example of Rob Skiba. We miss Rob, and showing, how if you simulate the atmosphere as a magnifier, you can have all the same behavior that we see in nature, including the horizon. I recreate this in computer, and what I'm doing here is I am not moving the camera. I just moving this black square, which simulate an atmosphere. And here you can see how buildings could amplify and getting smaller and being cut in the bottom part, because this is, I hope you see well, this is the bottom part of this area here in the geometric way, without considering the optic part. But when you render with an optics part, you're going to lose all the bottom part of these buildings. If I skip forward, we can see here in the big screen. And again, this is all geometry. And here is with the simulation of optics, changing the index of refraction and things like that. So this is what they call looming. And, here we have this, the news reporter trying to saying, okay, it's all based on semantics,
So technically speaking, this pic is looming.
So it's not the curvature of the Earth, it's just looming, right?
A mirage, but that's all semantics. It's all atmospheric refraction.
Okay, well, so the Earth is flat in that case, at least. Of course, we can explain, and this is a nice simulation too, with real objects, not in the simulation. We can explain the idea of the bottom part of the clouds being illuminating by reflection on the ground, and the angle of the light, it's bending in the atmosphere, and that is that we can have bottom parts of object illuminated without changing the altitude of the light source. But that is how perspective and light behave in a real world. So that is not a proof of a spherical world. Here we can see the comparison. And here you can see another example where you can see how the candle is going away, and when it's interact with this magnifying sheet, you can see how it's going to disappear in the horizon, quote unquote, without changing the altitude of the actual candle in this case. And like the Dr. Walter Lewin once explained, let's take this into account too, because it's not just refraction the problem, but also diffraction.
I want to address the issue of the angular resolution of your own eye. You can now calculate what the ultimate angular resolution is of your own eye, because you can estimate what the diameter is of the pupil, the opening of your eye. 3 millimeters, maybe 5 millimeters, a little bit larger at night when it is dark, pupil opens up. But we can calculate what this is. I think, though, that most of you will not be able to see with an angular resolution of 1/2 arcminute. Most of you are probably in the domain of 1 arcminute. It's a little larger than diffraction, but it's very close to that. When you think of diffraction, it's really an incredibly fascinating thing. Because what does diffraction actually mean? That it is a limitation that is put upon us, on everyone, also God. No one can bypass diffraction. This is Mother Nature. You cannot beat diffraction.
So we all need to lead with that. Why I'm talking about the gradient of or the angle of attack? Well, if you go even to actual document from NASA provided by NASA Astrophysics Data System, in one of the pages, this is the actual document, is called Understanding Astronomical Refraction. Here you can see this is just a scroll of the document. But when you reach this page, which is 91, I believe, you can see that they're trying to separate between the observation in terms of where it being produced is the same. Is here on Earth. We are looking from the ground to the sky. In some cases, up, but in some other cases, we look front, right? And what they say is that you need to have into consideration the astronomical refraction, which is the horizon refraction, as you need to take into consideration if you observe a boat in the distance, not just stars in the distance. But the idea behind is that they assume that the surface of where you are is flat, is a flat Earth, of course, between parentheses. Don't worry, Glover. But this is what they call astronomical refraction, which is insane because it's one refraction in this case. It's always the atmosphere that produces that distortion. Doesn't matter if you are looking stars of a building or a boat. But this is the gradient area that they're trying to say, hey, don't take into consideration what happened in these 20 degrees. This is the horizon line at 0 degrees, and you have 180. Okay, this is 90 degrees. Well, this area, this angle, don't take into consideration. And why that? Why is that? Because of course, when you put the camera, it doesn't matter if you are on the ground, if you are on the mountain or whatever, you're gonna have this distortion in that area. I showed before the Twin Towers example. Here, this is a sunset. We can show, for example, here in the Arctic, here in the case of the this piece of land that I showed before, the boat, the guy on the bicycle going into the fourth dimension of the horizon is going to disappear. So again, if you are up, for example, higher, this is like 3,000 meters near to an astronomical observatory, you can see how the star trail is going to, behave as almost in a linear fashion. But when it's entered in this angle of attack, immediately you're going to have that distortion. So it happened with real object, it happened with plasma or light of the stars, it happened with the sun, it happened with the moon. It's like Lewis said, nobody can bypass that type of diffraction of the light based on the angle of attack and the atmospheric conditions. So there is not any proof of a geometrical occlusion based on the curvature of the Earth that they're trying to tell us. This is one of the best cases in terms of the long distances from the ground, which is the Canigou. Here you can see what happened. You're going to see how the sun is going to stretch down in this case, and it's going to show the silhouette of Canigou. Sometimes, some days you can see more of the Canigou, some days you can see less of the Canigou, but none of the Canigou must be seen. And in fact, you can see some examples, the Looming with towering and mirage of Farallon Island. And here is the different days in different times. And you can see how you can produce the same effects of in New York, for example. So we have this idea that we can repeat the observation to infinity. And we can prove this all the time in different places, different days, different times, different atmosphere condition. But this is what is happening. This is not a floating island. Here is not the mirror Iceland. The real Iceland is this, but you need to have all these things into consideration, especially with the Canigou, because remember that in terms of the spectrum of light, you have the ultraviolet and the infrared spectrum, right? And the infrared is the lower in terms of the frequency in the cycles per second, and the ultraviolet is the fast one. So if you use the Doppler effects, you can see how the suns move, because in the sunset we have the lower down, the infrared, where the object is going and the light is stretching. And when we have the down, I think it's in English, in the morning, we can see the ultraviolet. The sky is tinted a little bit of violet until blue, until white, because the wavelength of the object moving, in this case the sun, is going to stretch because it's coming towards, and then it's going. And that is where the light wave is stretched, and that is what it happened in the sunsets and the dusk in this world. In this setup, you can understand what I'm trying to say. Sorry if I think my camera is also show. I hope that, because I am moving my hands trying to explain what I'm trying to say. So here the setup is like a Michael and Morrison experiment, but to see how the light behave and change based on the temperature of the surrounding area. Here you can see this is just a pointer, a laser point that is going to bounce and split and all the usual stuff with this type of setups. But the idea behind is that the final result is going to be projected in this screen here. This point light, this laser point, is going to pick, tack, and it's going to be in this screen the final result. What happened when you introduce, this is the typical and usual diffraction diffraction style of the light. What happened when you introduce heat in one area? Well, the light, quote unquote, is going to lower down, like you see, for example, with the sun in the horizon in the case of the Canigou. So the temperature play a huge role in this disappear object too. It's not just the distance or the angle of attack or things like that. So here you can see again, like how the temperature surrounding an area is going to appears an object to be lower than they are. Of course, we also talk about apparent position of some of things in the sky. But again, the problem that they have is that they cannot show things completely obscure appears to our eye level. Again, the tropospheric propagation forecast, you need to, it's not just a tiny area in some wild part of the world. This happens all the time. There is forecast for see the Fata Morgana thing and blah, blah, blah. I just showed this because it's not something that, well, that happened once in 200 years. No, that happened all the time in your local area, in other part of the world. You cannot bypass that type of thing. And of course, we also have here, this is a really long distance display of this is actually the moon. The sun is over here, and then you can see how the atmosphere bends the light, and that is what happened, bends the light. But there is a distinguished separation between which is the sky aerial perspective and what it is the ground perspective, how things works in the horizon and how things works outside of the influence of atmosphere. So we can explain, I'm gonna go a little fast because I don't have much time, and we can explain a lot of things based on the rotation of the stars, how the sun works and the horizon, why we see different rotation clockwise and anti-clockwise, depends of the orientation of the observer. It's not that the stars turns around, it's it's the stars, of course, moving in one direction, but the observer is who is inverted, and that is why we see different orientation or rotation in the south and in the north. We can also explain, how, let me just here, the anti-crepuscular rays, the crepuscular rays, all that kind of stuff. All you need is to take into consideration that the atmosphere, it produces this type of bending. For example, in this simulation, if a person inside of that personal dome see the sun moving, because it's the sun what is moving, you can see in that gradient, the sun is going to start cutting off and disappear in the horizon. But what is really happen if you have the chance to see from outside? Well, here you have the camera inside of that simulation. Imagine that this is a building and we have different outside cameras. This is the personal dome of influence, and here you can see that the sun, for example, in this case, it's almost touching the ground. You can see here, but it's never touching the ground, of course. It's always in the same line of altitude moving across the sky, but the idea of the arc that it's always used in astronomical studies, it's not based on the actual geometrical object of the Earth or the rotation of the Earth going backwards. It's our personal dome of experience. And here you can see how the sun is going to change elevation and appear elevations. Okay, look here, based on that personal atmospheric dome, and you cannot bypass that. It's impossible to bypass that. In fact, if I again simulate, you can see here how in this case, like without the glowing, the sun is going to disappear. But if I gain altitude, of course, it's going to rise up again from the horizon because I changed the angle of attack. And again, if I make a zoom, I can see that the sun is over the horizon. The sun continue its path to the horizon. It's going to disappear again. But when I rise again, the sun is going to appear again. And also the cloud, it's going to appear to touch the ground, which of course never happened. And if I zoom out, this is a completely 100% flat surface because it's created in a computer, but we can recreate that type of disappearing phenomena of the sun. In fact, this is what we're trying to say about when we talk about the apparent position of an object in the sky. Again, this is in a real simulation. You can recreate a circling sun without changing altitude. In this case, we are not talking about the analemma, but you can see how you can influence one area of light, the other it's night, based on how the atmosphere absorbs light, because it's something that happens. The air is not empty, and it's going to have the water is going to have an absorption of the light. It's going to slow down the light that is being produced by the sun. So again, here is a simulation where you can see how an object which is always at the same altitude circling the Earth, in this case the Gleason map, is going to appear from the ground that is occluding, is hidden by the horizon, but that is not what it happened. The problem is that we cannot go outside the system to see with our own eyes, and even our cameras, in terms of sounding rocket or stratospheric balloon, cannot reach the complete altitude to get out of the system. Remember that in the if you put a test the famous distance of the curvature of the Earth based of the distance to a mile square, the 8 inch per mile square, you're never gonna find the curvature of the Earth. Supposedly in this stratospheric balloon, the magenta area tinted here, this was calculated using AutoCAD. This must be the curvature of the Earth, and we can see the horizon at the eye level. Of course, this is 35 kilometers, but the official numbers is that you can see the curvature of the Earth at 15 kilometers supposedly, and we are here at the double, much more than double, and we cannot see that curvature. In fact, we see a local sun illuminating in the omnidirectional way. This is another examples of the high altitude balloon. Remember that every single lens, it doesn't matter if it's your eye on a camera, it's going to see in the circular way. You cannot avoid that there is not a rectilinear perfect lens. In fact, if you go to OptiWiki, you can see the resulting image will obviously circular. Always. If you transform some GoPro from a fisheye lens to rectilinear lens, you're going to have this stretchy behavior. But at the end, if you are in a big area of super nice atmospheric condition, you're going to see like a circular pattern, okay, circular shape, because that is how your eye or a lens behave. But a circular path is not a curvature. It's just that it's a flat circular path. Here you can see a stratospheric balloon, almost 40 kilometers from real life. And here, in comparison with the ISS, here you can see how, of course, the eye level of the horizon, etc., etc. But here you can see how the clouds are changing. It's a real video of the time lapse. In the ISS, you can see 4 hours of time lapse with the clouds not changing even 1 inch. And this is a compilation of video. So again, we have a lot of calculators to put on test the curvature of the Earth. We have the admission of the own creator of the MetaBank saying that they don't, well, listen.
This point by saying that you accept it based on the zoom. Do you still maintain that position?
It's the standard model. Sorry, the standard model has no scientific backing. Is that assumption correct? Well, it's the standard model. Sorry, the standard model has no scientific evidence. You only assume a value of R. Correct, Mick?
Yeah.
So there is no standard model. There is no standard refraction. That is a completely crazy global thing. Here is some paper when they trying to explain the quote unquote standard atmosphere refraction. There is, as is well known, the standard atmosphere is never found. Sorry. So again, we have the black swan in terms of a really lower camera almost at the ground level, and we can see farther away. Or you don't see, you don't need, you don't have the necessity to see forever to the edge of the world to prove that the Earth is flat. It's crazy thing in that way. We see, or we have example for Tolan using infrared lenses. We have the San Jacinto example. For example, you can go and check it on the Tolan Media One YouTube channel. We have all same cases here in Argentina. This is the skyline of Buenos Aires seen from Uruguay. 54 kilometers is around 200 meters of curvature, and we don't have even one building that pass the 200 meters. It's only one, and it passed to for 3 meters. So, and we can see a lot of buildings beyond the curvature of the Earth. Of course, here is a camera example. This is a little higher, it's like 6 meters, but again, we can see buildings not just belong to Buenos Aires, but also to near cities. And a lot of these buildings doesn't even have 100 meters, and we can see it, we can film it. And of course, you cannot see the bottom part based on all the other explication that I give. Of course, we have the famous Chicago skyline. Again, remember that no even one of these buildings go higher than the supposedly 548 meters that you need to see this. And we can see quite a lot of these buildings. We have the time lapse again, and you can see how even really lower light in the horizon is going to start appear at the night come. And this is just maybe buildings of 30 meters, 40 meters. So it's crazy to people still believe that this is something that happened because the curvature of the Earth. Of course, when you go up, at least in some example, you need to have the horizon lower down of your eye level, and that never happened. We have examples of Tolan filming object mountains to 1,000 kilometers to the horizon, which is 3 times what the globe predicts. And again, I really recommend the Tolan Media One channel, because it's crazy how much information this engineering has. And you can, see for yourself. I'm going to skip forward based on the time that I left to finish the presentation. But again, we don't have any evidence of the curvature of the Earth occluding anything. And here you can see some of the distant objects that this guy is capable to see with his infrared camera. Nobody debunks this, of course. And remember that in the case of our supposedly spherical world, at 10 kilometers, which is the altitude of a standard plane flight, you can see only 350 meters to the horizon, right? And this guy see 3 times this. So you don't have any chance. Again, if you go to sounding rockets, I have here a compilation. You always, if you correct the cameras, because unfortunately a lot of these sounding rockets are with GoPro, but if you start to compare, this is 30 kilometers, this is 120 kilometers, and the eye level and the horizon is at the same altitude, at the same eye level. So it doesn't matter how much you go, you're gonna always see the horizon rise with you, which is something that you cannot, at least in my opinion, you cannot have in a spherical geometry. If you rise up in the spherical geometry, at least in some part of the flight, you need to see the horizon go down, okay? And here we can see how immense the Earth is in comparison, of course, of with the sun, the moon, and other stuff that we can see. Of course, you're never gonna see the stars going up 40 kilometers. The sky is always black. It doesn't matter if the sun is there. You cannot adjust the camera to see at 120 kilometers the star, at least in all these space agency videos, they never show us the star, which is a really, really deep problem for the heliocentric model in terms of how the light behave in a vacuum. I am not going to address that, but remember that what I'm trying to say is that supposedly.
So that's why we have a blue sky.
Nice.
Now, it's also why you can't see stars in the daytime other than the sun.
Well,
It's not, oh, you can't see stars in the daytime because the sun is out. The reason why you can't see stars in the daytime is because the scattered blue light has rendered our atmosphere aglow. The atmosphere is glowing blue light. And that prevents you from seeing the stars behind you. If you took away the atmosphere,
you'd be able to look up and see the
the
sun.
sun will be different. Like dark and just over here, and there's two stars right over here.
Sorry, Neil, but that doesn't happen. So again, they are a really problem. In fact, these guys talk about take a look of this because it's crazy.
Whilst in space, have you ever looked away from Earth into the black void?
Oh, what? Yeah.
Because you can see the stars.
Oh, yeah.
And pretty much all the time you can see the stars.
It's not a black void. I mean, it's black, but there's all kinds of polka
There's all the stars there. The cool thing is about it, you can see it during the day.
Yeah, you can't end. There's more than stars. You can see planets.
Oh,
You can
Right.
see moons.
You see the gas, the Magellan clouds of
Yeah,
the
you
Milky
see
Way
the
galaxy.
Magellanic Clouds.
Magellanic. See, I
Yeah,
just
and
thought
then,
the
well, there's a
Magellan
large
clouds,
one
I
and
didn't
a
want to-
small one, right?
Yeah.
And then you can see the zodiacal.
okay, stop there, man. You can see Jesuit all over the place. And it's not based on how you adjust the lens and the aperture of the lens of the camera, because we have a civilian observation to contradict what these astronauts are saying, and that Grace Tyson too. Sorry, because this is in Spanish video, but William Shatner talked about when he took the flight with Jeff Bezos' Blue Origin, that everything happens so fast and you leave the atmosphere down there with the blue Mother Earth, and then the rest is completely black. And what is that? Is death? Is what I see. I expect to see stars, to see planet, but everything was black. And again, that is a very, very deep problem to the heliocentric model. I don't know how much time left, Jeran. If you can tell me, maybe I can address this final topic, or if not, I close here.
5 minutes.
5 minutes, okay. I simulate, I'm gonna go in very fast, but again, the sunset idea, how to explain this type of phenomena that we can observe in nature, which is cloud touching the horizon, the sun cut off in the horizon, and also the appearance that the sun it's between mixed with clouds and all that kind of stuff that you are already seeing. So I create like a tiny piece of atmosphere. This white rectangle is going to simulate clouds, and this spherical representation is going to be the sun. Of course, this is in the geometric way because that is how our 3D software works today. Then you need to press render, and it's gonna, the magic is when the magic happens. I create the beach, and the black part is the water, right? Trying to simulate the conditions of the actual video showing how nature works. So I create the temperature gradients, how everything's behave. We all know that the clouds, it's a layer, it's a flat layer. That is why I recreate this flat rectangle, and that tiny point is going to be the cloud. So when you render this, let me just skip forward. When you render this, what you're going to happen is I move the sun in a linear fashion, always above the clouds, above the ground. It's never went down, never ever changed altitude. It's just a local movement trying to simulate the sunset. Okay, so when you press enter, you have this. You have water, the beach, the clouds, and a tiny area illuminating, because of course the sun is local at least in the flat Earth model and in the real life. So when I move, you can see here how the lights move. When I move forward the sun, of course, the cloud is going to start getting more dark because the light is gone with the sun. Okay. So again, here you can see how the lights behave. And if I make a zoom, for example, I'm going to start to see this type of behavior. The sun is still above the horizon, not the clouds, but it's starting to mix with the cloud. But remember that the sun and the clouds are not bending into a curve. It's always a flat thing, but all these conditions in the atmosphere is going to give us the appearance of that bend. If I make a zoom, I can see even how everything can be simulated on the flat surfaces. You have the cloud touching the horizon, like in the real life. You have the mix between the sun and the clouds, but it's not an actual mix. Of course, every object is really separated one with another, but the behavior in the atmosphere is going to produce that. In fact, here you can see an example, which is you have a film and you have a light behind it, and it's going to appear that the film, which is in front of the light, because the light is in the back of the cardboard, is going to appear to be mixed. But that is for the intensity and because the object has transparency as the cloud in the real life. So coming again here, if I reproduce that, you can see how when I move the sun in the forward, in a linear forward without changing altitude, is going to appear to change altitude. And when I proceed, I render this, you can see here is the sun above the clouds, above the horizon. Then when I re-render, it's going to see that the lights go with the sun and the sun disappear in the horizon. But if I make a zoom, again, let me just make a zoom in the geometrical world. The sun is above the horizon, is above the clouds. And remember that these tiny points are the clouds when simulated. And when I hit render, the sun, which is here, is going to appear with the refraction touching the horizon and be cut off. This is the actual setup with the sun above the line of the clouds and above the horizon, which is the suelo, the ground. But in the render, when you have into consideration, the refraction is going to appear to be cut off in the middle of the horizon, mixed with the cloud, etc., etc. So again, here is the real life example, and this is my simulation, and you can see how much perfectly. So you don't need a spherical geometry to recreate the sunset. It's completely possible to do it in the flat surface. So I'm going to skip forward very quickly. We have some example here of the sun going to the horizon, getting away from our view in the linear fashion. For example, here you can see like a straight line, and the shadows of the cloud is going to, produce because the light of the sun is going away, etc., etc. Sorry for my fast presentation in this part, but what I wanted to say is that we can recreate all that stuff. Even remember that the sun is a local focal point. We are not seeing the actual sun. We are seeing maybe the focal point that it's being produced in the atmosphere. Again, this is a very fascinating topic. We can talk about the electricity being involved in the color of the sunset, the electrical universe, and things like that. But we are going to leave that for the next summit, because I hope Jaron and Austin invite me again to participate. So thank you so much, and I hope you understand everything I said.
Your English is getting better, my friend. Don't you worry. And none of us can speak Spanish as well as you speak English, so just remember that. Well, not none of us. I can't really speak for everybody, but for myself, certainly.
Okay, but that is not a consuelo. I don't know how to say in English.
Consuelo. Consolation?
Consolation, yes.
Yes, okay, yes. Gotcha. All right, thank you.